Good afternoon, ladies and gentlemen. Welcome to the International Prague seminar on function spaces. Our today's speaker is Óscar Domínguez, and he will talk about estimates for maximal functions and applications. The stage is yours.
So thank you very much for the introduction, and also let me thank the organizers for the very kind invitation. I'm very happy to be part of this seminar and to give a talk here. Today I will talk about maximal functions and some applications. This talk lies at the intersection between harmonic analysis and theory of function spaces, and it's based on joint work with Sergei Tikhonov, ICREA, from Barcelona. Let me start. So I will start from the scratch. So in this talk, by Q and Q naught, we always mean cubes in the d-dimensional Euclidean space with size parallel to the axis of coordinates. Let me recall you the definition of BMO space. So we say that a local interval function has bounded mean oscillation if this condition is satisfied. Or in other words, the mean oscillation of the function f are uniformly bounded with respect to all cubes contained in Rd. Here, as usual, we denote by fq the integral mean of the function f related to the cube q. This space was introduced in the seminal paper by John Nirenberg in '61, and in connection with certain questions arising in elasticity theory. But it was soon realized that BMO is a very important space in many areas of analysis. So, for instance, in '61, Moser was able to adapt some ideas from John Nirenberg in order to establish Harnack inequalities for non-negative solutions of elliptic PDE. Also, it's well known that BMO acts as a good replacement of L infinity in many situations when L infinity does not work. For instance, this happens with the Hilbert transform. Everybody knows that the Hilbert transform is not bounded on L infinity, but if you enlarge a little bit the target space, I mean, if you go from L infinity into BMO, then you can get boundedness of the Hilbert transform from L infinity into a BMO. In the middle of the 60s, people started to investigate the role played by BMO in interpolation theory. And in particular, Stampacchia and Campanato proved that BMO is a good extreme space to apply interpolation theory. So, roughly speaking, interpolating between LP and L infinity is equivalent to interpolating between LP and BMO. As I already mentioned, this is very useful in applications because many classical operators in harmonic analysis fail to be bounded on L infinity, but they are bounded on BMO. So one can use the machinery of interpolation theory in connection with BMO. I will say that a striking point in the theory of BMO came in '71 when Pfefferman obtained his famous duality theorem. I mean, the dual of BMO can be characterized as the dual space of the Hardy space. And in '72, Pfefferman and Stein were able to develop real variable approach to the theory of Hardy spaces and in connection with Carlson measure estimates. Also in the '70s, people started to investigate the space BMO from a probabilistic point of view. Here you can replace the mean oscillations by certain martingales, and then you can mimic the definition of BMO, but now from a probabilistic point of view, and this was mainly developed by Garcia and his school in the 70s. So BMO is a very important space, very interesting, and I will say that the main result contained in the paper by John Nirenberg refers to a certain inequality. This inequality can be rephrased in terms of embeddings between function spaces. So in this talk, by this arrow, we mean that the identity operator is continuous. So John and Nirenberg prove that BNO is very close to L infinity. And to be more precise, BNO is contained in the Orlik space of exponentially integrable functions. So I am not going to write down the precise definition of this Orlik space. I think this is well known for this audience, but you can introduce these spaces, this space via Luxembourg norms, but let me omit this. What is more interesting for me is that this space is very close to L infinity in the following sense. So it is contained in L infinity, and on the other hand, it contains L infinity, and on the other hand, it is contained in all Lebesgue spaces LP with P less than infinity. As a consequence of the John Nirenberg inequality and this embedding, one derives a prototype of self-improving property in analysis. Namely, if you start with a function in BNO, just from the definition, we only know that the function is L1. But a posteriori, because we have this condition, we can get better integrability properties of the function. And we get that the function belongs to all Lebesgue spaces LP with P less than infinity. In general, it is rather complicated question to obtain a simple criteria to identify BNO functions. Of course, one can make use of the Pfefferman duality theorem together with Hardy type inequalities in order to obtain characterizations of the BNO seminor for Fourier series with positive coefficients. But in practice, this can be quite difficult to implement. So it is interesting to obtain say, simple criteria to identify BNO functions if for special classes of functions. And in particular, this can be done if you are working with power series. This was done by Colliada and Lendler in 1998, or more recently, Chamizo, Cordova, and Ubis were able to obtain a simple criteria for BNO functions when you are dealing with lacunary Fourier series. And as a consequence, they are able to obtain nice consequences in number theory. So the summary of this last statement is that we need some embeddings in terms of more familiar function spaces into BNO. So how can we ensure that your function belongs to BNO in terms of more familiar function spaces? Let me recall you a very classical statement in terms of fractional Sobolev spaces. Before, I would like to recall you very briefly the definition of fractional Sobolev spaces. So here, we are considering smoothness S, a real number, and P is strictly less than 1, strictly larger than 1, strictly less than infinity. In this talk, I'm only interested in homogeneous spaces, so let me omit the dot above the H, so this will be interpreted adequately, so we always work with homogeneous spaces. One can define the fractional Sobolev space as the closure of the Schwarz functions modulo polynomials under this seminor. So we take the LP node of the fractional Laplacian of F. In the so-called critical case in Sobolev inequalities, I mean, when the smoothness coincides with dimension divided by the integrability, it is well known that the corresponding Sobolev space is not formed by bounded functions. However, as we already mentioned in the introduction, if you replace L infinity by the slightly larger BNO space, then you can get the embedding into BNO. So as a consequence, if your function belongs to the Sobolev space with critical smoothness, then your function is automatically in BNO. But now the natural question is the following. So how sharp is this embedding? So can we improve this embedding? The answer is yes, and let me give you at least 3 different alternatives to sharpen this embedding. So the first way that I'm going to report deals with BSOF spaces. I think that BSOF spaces are also well known in this community. For people in this audience. But anyway, let me recall you the definition very briefly. There are several ways to introduce BSOF spaces in the literature, but in this talk, I'm interested in dealing with BSOF spaces given in terms of differences of moduli of smoothness. So given K is a natural number, we denote by omega K of FTP the kth order moduli of smoothness of a p-interval function f. I mean, we consider the LP norms of the iterated difference of order k with step h, and we take the sum over all possible steps with length less than or equal to t. So this is a very useful tool in approximation theory. And as usual, the first difference is given in a standard way. One can introduce iterated differences via induction. Here, the parameter k is related to the smoothness of your function, and clearly, if you increase the order, then you are able to get better estimates. Using the model of smoothness, one can introduce BSOF spaces. So here we have 3 parameters. So S is positive and it is related to the smoothness of your functions. P is related to the integrability, and Q is the so-called fine index or summability index. So roughly speaking, we say that the function f belongs to this BSOF space if the module of smoothness has a certain decay near 0 and near to infinity in order to get that this integral is convergent. Here, k is strictly larger than s. One can prove that this definition is independent of k with equivalent seminors. As usual, if q is equal to infinity in this definition, one should replace the integral from 0 to infinity by the sum over all t greater than 0 of this expression. The second index q in BSOF spaces plays a key role dealing with embeddings because it enables us to sharpen results. And in particular, the scale of BSOF spaces is monotone with respect to the second index. So the largest possible BSOF space with fixed smoothness and integrability occurs if q is equal to infinity. So, and indeed, one can prove also a classical result that dealing with BSOF spaces with second index infinity, this BSOF space is embedded into BNO. And on the other hand, this space contains the classical Sobolev space. So one can improve the Sobolev embedding in terms of standard Sobolev spaces via BSOF spaces with the help of the second index in BSOF spaces. Now let me recall you a second alternative to embeddings into BNO. And the philosophy of this second alternative can be summarized in the following statement, going from Lebesgue to Lorentz spaces. So in recent times, there is a growing interest in working with smooth function spaces based on Lorentz spaces, because they provide optimal answers to some outstanding questions in analysis. For instance, let me mention only a few references. Goatis, Billy, Opitz, the Horn of Travels obtain a wide variety of Ulyanov type inequalities using Lorentz and Lorentz-Zygmunt spaces. Seeger and Travels obtain a full characterization of embeddings between Biesov and trivially sorting spaces based on Lorentz spaces. Or Grafakos, Slavikova obtain Sharp-Horn-Mandel multiplier theorems via Lorentz-Sobolev spaces, or much more recently, Bressis, Van Safting, and Young obtain an interesting characterization of standard Sobolev spaces without invoking derivatives, and going from LP to Greek LP in the corresponding Gagliardo seminars. But before going further, so just for convenience, let me recall you the definition of Lorentz spaces, LPQ. So the Lorentz spaces can be understood as a generalization of Lebesgue spaces, and with the help of this second parameter, say Q, one can get better estimates. So here, this is the quasi-node defining Lorentz spaces. So roughly speaking, you need that the non-inclusion rearrangement of your function behaves like t to the power -1 over p with an additional decay near 0 and infinity in order to get that this condition is satisfied. As usual, if q is equal to infinity, we have to replace the integral by the sub, and these spaces are also known in the literature as Greek LP spaces, or they are Marcinkiewicz spaces. As I said, the scale of Lorentz spaces consists of a refinement of classical Lebesgue spaces, and the scale of Lorentz spaces is monotone with respect to the second parameter. So the largest possible Lorentz space is the Greek LP space, and in the special case that Q is equal to P in this definition, we recover the Lebesgue space LP. So a classical result obtained by Stein and Zygmunt in 1967 asserts that if you go from classical Sobolev spaces to Greek type Sobolev spaces, I mean only replace in the classical definition LP by Greek LP, then you get a larger space, but still you are working with BNO functions. So here you can improve the classical result via Greek type Sobolev spaces. In the special case that this smoothness is integral, since p is strictly larger than 1 and less than infinity, one can make use of the mapping properties of the Riesz transforms to get that this space coincides with the standard Sobolev spaces based on Greek LP. In the special case that this smoothness is equal to 1, one can use Polya-Sego principles, and then Chunky and Peak show that this embedding is optimal working with the class of Sobolev spaces based on rearrangement invariant spaces. They obtain more results when you replace here BNO by L infinity or vanishing mean oscillation. So working with the pool of competitors given by Sobolev spaces based on rearrangement invariant, you cannot improve this result. But what happens if you change the competitors? So let's see. So there is a third alternative that I would like to explain today, and this is based on Calderon-Campanato spaces. So this is another way of introducing fractional smoothness spaces. the definition relies on fractional sharp maximal functions. So here alpha is between 0 and 1 can introduce the fractional sharp maximal function as the sum over all cubes containing the point x, and then we consider the fractional variance of mean oscillations. In the special case that alpha is equal to 0 in this definition, one recovers the classical sharp maximal function by Pfefferman-Stein. And with the help of these maximal functions, one can introduce the so-called Calderon-Campanato spaces, C alpha P, with smoothness alpha and integrability P. So these spaces are very useful in harmonic analysis and also in PDEs or in analysis of metric measure spaces. Let me mention that this scale of function spaces contains many distinguished examples of classical function spaces. So without further details, let me say that BMO, Helder spaces, LP, standard Sobolev spaces, or triple Lysorkin spaces are special cases of Calderon-Campanato spaces. And in general, we have embeddings between Calderon-Campanato spaces and Biesov spaces and fractional Sobolev spaces. And these embeddings are sharp in general. You cannot improve the parameters here or here, so this is sharp. I would like to refer to the memoirs by the Bohr-Shapley from '84 for proofs of these results and further statements. Somehow hidden among the pages of these memoirs by the Bohr-Shapley, you may find the following interesting embedding. So if you deal with weak type Calderon-Campanato spaces, I mean, if you replace LP by weak LP in the classical definition, and you are working with the fractional, with the critical smoothness, then you get embedding into BMO. Of course, this space contains classical standard Sobolev spaces. So this is a third alternative to improve the starting point of our talk. So far, to summarize, we have considered three different routes to deal with embeddings into BMO, namely Biesov spaces with the help of the find index, weak type Sobolev spaces, and weak type Calderon-Campanato spaces. But the question is, can we unify all these approaches? More interestingly, can we improve all these embeddings? Because again, dealing with optimality assertions, it's very important to fix what is the pool of competitors, right? We are dealing with. So let's see. So the first result that I would like to present you in this talk answers the previous questions, and it is based on weak type Biesov spaces. So the idea is to combine both methods. I mean, to combine the Biesov, the strength given by the second index in Biesov spaces, by the find index, together with the strength given by going from LP to weak LP spaces. So using this idea, one can introduce in a natural fashion weak type Biesov spaces. So you only need to replace in the classical definition LP norms by weak LP norms, or if you prefer by differences. This is equivalent. And then if P is strictly larger than 1, less than infinity, together with Tikhonov, we prove that the weak type Biesov space is embedded into BMO. Before I give you some ideas about the proof of this result, let me mention some consequences, because This embedding theorem improves all known results. I mean, this space contains at the same time classical Bieshov spaces, weak-type Sobolev spaces, and weak-type Calderon-Campanato spaces. And furthermore, this embedding is strict. I mean, this space is strictly larger than these spaces. And as an interesting remark is that here we have a restriction on the parameter p. Of course, the case when p is less than or equal to 1 is also true via Sobolev embeddings between Bieshov spaces. But what happens in the limiting case when p is equal to infinity? So if p is equal to infinity, at least formally, here you will have 0 and here you have infinity. So you are dealing with the Bieshov space with a smoothness 0, B0 infinity infinity. And in this limiting case, the result is not true. And in fact, you get the converse embedding. This is also well-known embedding if p is equal to infinity. But here, be very careful because you are dealing with Bieshov space with a smoothness 0 given by the Fourier transform. Because working with a smoothness 0 is a quite delicate question because standard approaches to introduce Bieshov spaces usually differ dealing with the smoothness 0. So dealing with the smoothness 0 is very important to fix what is your method to deal with Bieshov spaces. So here we are dealing with Fourier analytically defined Bieshov spaces. So this means that the norm of this embedding blows up as p goes to infinity in this result. Right. Yes, and now I would like to say some words about the proof of this embedding. Our method relies on sharp pointwise estimates for maximal functions. So to motivate our method, let me start from very classical results. So let me recall you again the classical embedding into B and O in terms of classical Bieshov spaces. So this is a, say, qualitative result, but now we are interested in the quantitative version of this embedding. Or in other words, we are looking for pointwise estimates involving the sharp maximal function and the moduli of smoothness. And in the special case that we are dealing with a one-dimensional setting and with smoothness 1, the board in 81 was able to obtain this very nice inequality. Know that once you know this inequality, this embedding follows immediately because you only need to take the limit as t goes to 0 on both sides of this inequality, and then here this will be the L infinity norm of the sharp maximal function, I mean the B and O semi-norm, and on the other hand, if t is equal to 0, this is exactly the Bieshov semi-norm. So this is a stronger statement than this embedding. And furthermore, this inequality also holds true in the borderline case when p is equal to 1. And in this case, you can go further and you can remove this sub given on the right-hand side. But this is an immediate consequence of the fact that the moduli of smoothness is a quasi-concave function. So here, you get better result if p is equal to 1. And this inequality can be considered as the quantitative version of the classical embedding in the univariate setting from bounded variation into BMO. Indeed, you only need to divide both sides of this inequality by t and take the sub over all t greater than 0 on both sides of this estimate, and then you will arrive at this embedding. All right, so, but here there are something that it can be improved. To be more precise, starting from the late 80s, Koliada and his collaborators did many interesting contributions to this topic. In particular, let me highlight the following estimate due to Koliada and Lerner in 2005 where they were able to improve the Bohr estimate in the special case that p is equal to 1. So in this case, so they were able to replace the sharp maximal function by the maximal function itself. And know that this maximal function is larger than the sharp maximal function. And this is an immediate consequence of the Hertz estimate. So, but this result is again in the univariate setting. And now, what happens in the multivariate setting? To the best of my knowledge, the best known result in this direction may be found in this paper by Kolyada from '89, where he proved that we can extend this inequality to higher dimensions, but we have to pay with this additional term on the right-hand side, 3 times the L1 naught of the function, at least for the small values of t. So some questions are arising here. Let me pose these questions. So the first question is, can we improve the Bohr inequality for p larger than 1? And in particular, what happens with the multivariate setting of the Bohr inequality? Or what happens in the Bohr inequality if we are interested here in higher order smoothness? Recall that if you increase the order, you get better and better estimates. Concerning the limiting case when p is equal to 1, I mean the Kolyada inequality, so this inequality, can we improve this inequality? And to be more precise, are we able to remove this extra term given on the right-hand side? Or again, can we deal here with higher order smoothness? So the next result provides us an answer to these questions, and it says the following. So consider any module of any order in the module of smoothness, any t greater than 0, and any dimension. So if your function belongs to the Lorentz space with p strictly larger than 1 and q is free, then we have to distinguish 2 possible situations. Firstly, if the smoothness is strictly larger than the critical exponent, then we can obtain this pointwise estimate. On the other hand, if the smoothness is less than or equal the Sobolev exponent, we can improve the previous estimate and we can remove this sub on the right-hand side and obtain this inequality. In the limiting case when p is equal to 1, we indeed are able to improve Kolyada inequality by removing this extra term here. And of course, we also incorporate higher order moduli of smoothness. So this is better than if you have here d equals 1. If this is larger than 1, of course. All right, so the proofs of these inequalities are a little bit technical. You need to use embedding theorems. You need to use different categorizations of Lorentz-Sobolev spaces in terms of differences as a Fourier transform, because we are using harmonic analysis techniques here. But okay, I don't have time to give you the proof, but at least I would like to mention some consequences of these pointwise estimates. The first remark is that if we take q equals infinity here, so we have here to replace the integral by the sub, sorry, here. So we have this inequality. So this provides us a quantitative version of the desired embedding. So the embedding that I stated in the previous section follows immediately from this pointwise estimate. Indeed, since this sub is obviously larger than when u is equal to t to the power d, so we arrive at this, and here we only need to take the limit as t approaches 0 on both sides of this inequality to arrive at this invariant. So this invariant is an immediate consequence of this inequality. And now, what happens if we take Q equals P in our abstract result? So if Q is equal to P, we arrive at this point-wise estimate. And now I claim that this is an improvement of the Debord inequality in the following sense. Since here we're dealing with no increasing rearrangement, we can make use of monotonicity properties, and clearly this the left-hand side is larger than this. And in the special case that D and K are equals to 1, this coincides exactly with the Debord estimate. So our estimate implies the Debord estimate. But we can go further beyond, and we can assert that this inequality is a non-trivial improvement of the Debord inequality. And let me make this assertion more precise in the following theorem. So we are able to construct a sufficiently large family of extremal functions such that we get equivalence in our inequality, but however, working with the Debord inequality, the left-hand side is far away from the right-hand side. Or in other words, when t approaches 0, this guy goes to 0 much faster than the right-hand side. So this is optimal, but this is far from being optimal, right? Here, by sufficiently large, I mean we consider Fourier series with general monotone coefficients. And the class of general monotone coefficients contains, of course, decreasing sequences or quasi-decreasing sequences, but also increasing sequences satisfying doubling properties, and even much more sophisticated examples. So this class of extremal functions is a rich class, right? So the proof of this result is, it takes some pages, because note that in order to obtain these statements, you need to control at the same time for the function f, the modulus of smoothness, and the sharp maximal function. And in general, this is quite challenging, but in the paper you can see the details. Let's go further, and now let me concentrate on the special case that p is equal 1. So we have obtained this inequality, and again this inequality is optimal in the sense that there exists a sufficiently large class of extremal functions such that the converse inequality also holds true. At this point, I think it's quite convenient to compare our results with earlier results due to Colliada in '87 for the special case that we are dealing with Lebesgue spaces. I mean, Q is equal to P, and K, the modulus of smoothness, is of order 1. So in this setting, he obtained the following point-wise estimate. Note that the sum given on the left-hand side is not the standard sum. Here, we may omit many terms because we have this additional constraint. So since we are dealing with no increasing rearrangement, we are considering only the terms n such that the sharp maximal function has a doubling property in a certain sense. So this guy may be quite smaller than the standard sum. And in the special case that the integrability is strictly less than the dimension, Colliada was able to improve the previous estimate after removing this additional constraint and working with the standard sum. So now compare these two estimates with our results. To to proceed with, it's quite convenient to rewrite our estimates involving integrals in terms of sums. But this is very easy because we can make use of monotonicity properties. So first, let us concentrate on, I would say, the most interesting case, I mean, when the integrability is strictly larger than the dimension. So in this case, our left-hand side is better than the left-hand side in Coliada, because here we're dealing with the standard sum. On the other hand, dealing with the right-hand side, Coliada is better because he's able to remove this sub on the right-hand side. Concerning the case that D is strictly larger than P, both inequalities coincide. We give a completely different approach to this inequality, so we are not relying on the techniques given by Coliada, but we arrive at the same result if P is strictly less than D. But our result also covers the extreme case when D is equal to P, which was left open in this paper. So at this point, a natural question arises. So the idea is the following. So let us concentrate on this case. So if P is strictly larger than D. So as I said, our method is better dealing with the left-hand side, but on the other hand, Coliada method is better dealing with the right-hand side. So the question is, can we somehow combine both methods in some way in order to win on both sides? I mean, can we obtain this inequality? Or in other words, can we extend this inequality for all values of P? And the answer is, unfortunately, is no. In the paper, we are able to prove that if you go to our inequality and remove here the sub on the right-hand side, this inequality fails to be true dramatically. So one cannot overlook the influence of this sub on the right-hand side. All right. Somehow related topic is Bennett-DeVos-Sharpley method to BNO. In this section, to avoid unnecessary complications, let me switch from the global case to the local case. So you may think that Q0 is, if you wish, the unit cube, and then we are dealing with the local variant of the Sharp maximal function. So here we restrict our attention only to the cubes contained in the original cube, Q0. And now we are, instead of comparing the module of smoothness and the Sharp maximal function, now we are interested in comparing the Sharp maximal function with the function f itself. It is an immediate consequence of Hertz estimate, as I already mentioned at the very beginning, that you can control the rearrangement of the Sharp maximal function via the maximal function itself. But what about converse estimates? I mean, assume that you know the decay properties of the Sharp maximal function. What kind of information can you gain about the function f itself? The answer in the famous work by Bennett-DeVos-Sharpley from '81, they prove that there exists a purely dimensional constant C such that this inequality holds true at least for the small values of t. So here, on the left-hand side, you are dealing with the oscillation of the function. And this inequality plays a key role in the theory of function spaces, working with envelopes, and it has been extended to many different situations, working with another maximal functions on the right-hand side. So it's a very important inequality, and also in the setting of metric measure spaces. In particular, this inequality gives us a refinement of the classical John-Nirenberg inequality. More precisely, if you take sub over all t greater than 0 on both sides of this inequality, you arrive at this invariant, BNO is embedded into this space. And this space is not L infinity. This is usually called weak L infinity, and here you can see the definition of the space. This is the supremum of the oscillations of the function. Furthermore, Bennett-de-Bord-Shapley showed that this space is indeed the rearrangement invariant set of BNO. And in particular, this space is contained in the exponential class, so that this embedding improves the classical John-Nirenberg inequality. But be careful here, because this space is non-linear. So this embedding does not contradict the well-known fact that the exponential class is the best possible rearrangement invariant space containing BNO, because weak L infinity is not a vector space. And now we obtain the following logarithmic variant of this the Bennett-de-Bord-Shapley inequality. To be more precise, we obtain this inequality here. The difference is that instead of working with the oscillations of the left-hand side, we only deal with the function f itself. Of course, we have to subtract here the average to avoid problems with constant functions. So for every t greater than 0 and any p between 1 and infinity, if your function f belongs to LP, then this pointwise estimate holds true. But note that working with the left-hand side integral, here you have a strange phenomenon. Here, instead of working with the integral from 0 to t, you have the log here. So you have a shift in the interval of integration. And here, you are dealing with a smaller interval than 0t. So what is happening here? So can we remove this guy, or at least put this here inside? No, this is optimal. So in the paper, we prove that the best possible value that you can put here is indeed when lambda is equal to p. So here you cannot put only integral from 0 to t, because otherwise this inequality is false. So you can find counterexamples. Let me say that this inequality may be considered as a quantitative version of the celebrated Pfeffer-Manstein inequality. So Pfeffer-Manstein inequality tells us that you are able to control the Lebesgue norm of the function by the Lebesgue norm of the sharp maximal function. So here, if you go to our inequality and take the limit as t goes to 1 on both sides of this inequality, then here you immediately get the Pfeffer-Manstein inequality. So this is a stronger assertion than the Pfeffer-Manstein inequality. One can also deal here in this result with the quasi-Banach setting, and also with the limiting case when p is equal to infinity. But in this case, the result looks more technical, because one should switch from standard maximal functions to certain variants, the so-called Stromberg-Jauer-Torczynski maximal functions. So I prefer to skip this part and only to concentrate in the Banach setting, when p is strictly larger than 1 and less than infinity. And in particular, we make a strong use of this inequality in order to manage this counterexample. So in order to control this guy from below, we make a strong use of this inequality. And note that it's not clear, at least for us, how to get the similar results only using this oscillation estimate, because the left-hand side is quite difficult to compute. I mean, if you take a Fourier series, try to compute this left-hand side for a special choice of Fourier series. This is, for me, quite challenging, but however, here you are in a much better position. So it's certainly true that you are dealing here with a weak type inequality because you are involving integrals, but on the other hand, you are dealing with a much easier function instead of oscillations. All right. And now in the last 5 minutes, I would like to give you of this from 79. So at least for the small values of t, Bennett Sharping obtained the somehow related to our estimate, but they don't have logarithms. But know that the Bennett-Sharping inequality is not optimal as t approaches 0, which is the most interesting case, even for smooth functions. Because if you take limits as t approaches 0 on both sides of this inequality, the left-hand side goes to the n infinity norm, and on the other hand, the right-hand side is infinity, unless that the function is constant. So this inequality is not useful as t approaches 0, but however, this phenomenon is not observed in our estimate. It goes to 0, you go to 0, and also you go to 0 on the right-hand side. As I said, let me give you some applications of this logarithmic de Bennett-Sharping inequality to harmonic analysis, and in particular, Pfefferman-Stein type inequalities. So here I'm recalling you again the classical Pfefferman-Stein inequality. This inequality, it has many important applications in harmonic analysis and interpolation theory. There are nowadays many different proofs of this inequality via good lambda inequalities or via duality theory, or as I mentioned before, here we have another proof, right? A quantitative version, in fact. And this result has been extended in many different directions. For instance, one can replace here this maximal function by another variance, for instance, the Stromberg-Jauer-Torczynski maximal operator, or one can replace the Lebesgue measure by weights, or more or related questions. And in particular, in this talk, I'm interested in the following question. So what happens if you replace here LP by another function space? In particular, this dealing with rearrangement invariant spaces, this question was considered recently by Stasky and Millman and also by Lerner, and they prove independently that if you consider any rearrangement invariant space X, the Pfefferman-Stein inequality, here replacing LP by X, holds true if and only if the corresponding lower void index is positive. I am not going to define here indices of function spaces, but roughly speaking, this means that this space X is not very close to L infinity. So, of course, because working here with L infinity, this is an enemy for Pfefferman-Stein, because the right-hand side will be BNO and the left-hand side will be L infinity. And we know that BNO is not contained in L infinity, right? Take logarithms. So once you are far away from L infinity, everything is fine, and then you get Pfefferman-Stein inequalities. But let me insist on the case when you are close to L infinity, because there are many important function spaces in harmonic analysis close to L infinity. For instance, the Orlik space given by exponential classes. So these spaces, as we saw, arise naturally in John-Nirenberg inequalities. Or for instance, this special class of Lorentz-Zsigmond spaces, also known in the literature as Bressis-Wenger-Hanson spaces, they are very useful in connection with critical Sobolev inequalities. So what happens in this space? Of course, you cannot expect to have here a domain if we know that your sharp maximal function belongs to this Orlik space. What happens with the function f itself? What kind of information can we expect? And this is the topic of the last slide, so limiting Pfeffer-Manstein inequalities. Here, I'm recalling you the definition of this special case of Lorentz-Simon space with first index infinity. So, roughly speaking, you are dealing with functions with logarithmic singularities only. In the special case that q is equal to infinity here, so here you have the sub over all t greater than 0, and then you can prove that this is concise with the exponential class. So applying the logarithmic variant of the Bennett-Bosworth inequality that we have obtained, we can obtain Pfeffer-Manstein type inequalities for these spaces. So if your sharp maximal function belongs to this space, then the function f belongs to this Rensmann invariant space. If you are familiar with the so-called Grant-Leveque spaces or gamma spaces, this space is a special case of gamma space. But I will not go into details, and let me say that this result is optimal. So all the parameters here, this logarithm, so it cannot be improved. So this is the best result that you can obtain here. In the special case that q is equal to infinity in this result, so you are dealing with the exponential class, and then here you have to replace integral by sub, so you can use some kind of Fubini type arguments, and you arrive at this result. So if your function, if you know that the sharp maximal function belongs to this Orlick space, then the function f belongs to this Orlick space. But there is a shift, as we know that should be, because otherwise the result is false. Here you cannot have the same space. And the shift is given by this parameter, lambda divided by lambda plus 1. And this inequality is optimal, so you cannot improve this shift here. There are more applications of this kind of techniques to different questions, for instance, to deal with Calderon-Scott type results or extrapolation estimates, but I think this is too much. I will stop here. Let me thank you for listening. Now I will be happy to try to answer your questions if you have.